Alright kiddos, welcome back, and we're continuing our discussion on neutralization reactions. In the previous video we wrote molecular, ionic, and non-ionic equations for different types of acid-base reactions. Today we are going to quantify those. What I mean by that is we're going to do some stoichiometry. These are often called acid-base titrations. And at the end of this video, I'm going to do an actual titration for you. You'll see a nice little demonstration, and hopefully it might make some sense. Now, for this, we need to remember a couple of things. Number one is remember back earlier this year that the product of molarity and volume is moles. Now, molarity has the unit moles per liter. When I multiply it by the volume in liters, liters cancel out and I'm left with the unit moles. So when we do our stoichiometry, remember at one point we need to get into the unit moles. And for these types of calculations we will normally multiply the molarity of the solution by its volume in liters. Alright, now with that background, let me go through the 4 steps in these problems. Number one, just like in all stoichiometry problems, we balance the equation. Number 2, we get into moles. Now, previously, we've gone from grams to moles, remember? And we might still have to do that on some of these problems, but oftentimes we'll be taking molarity times volume. After we get into moles of what we know, we're going to hop into moles of what we're after, and then we're going to get into our appropriate unit at the end. Now, the best way to teach this is just by doing a few examples. So, we're going to do a couple for you. Example 12, you're going to have one just like this on your upcoming assignment. So, pay careful attention and take really, really good notes. Now, I'm going to read the problem to you, and I don't think it's going to make a whole lot of sense. But then, we'll go through the 4 steps, and we'll arrive at our answer, and hopefully you'll have an aha moment. Alrighty? So, what would be the molarity of a potassium hydroxide solution if 15.6 milliliters of it is neutralized by 41.6 milliliters of 0.1 molar nitric acid? So, am I right? Did that just sound like blah, 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 blah? Yeah, I thought so. So let's just follow the steps and see if we can arrive at an answer. Step 1. Balance the equation. So let's write the equation first of all. We have KOH and HNO3. Now these are all double replacement reactions. So the K plus will get together with the NO3 negative to form KNO3, and the H plus will get together with the OH minus to form our favorite compound, water. So you can see this equation's a nice, pretty 1-to-1 to 1-to-1 mole ratio. Now, step 2. Let's get into moles. Now we're probably going to take molarity times volume. So let's see what I know the molarity and volume of. I know the volume of the KOH solution, but I don't know its molarity. That's the question after all. But for the nitric acid, I know its molarity, and I also know its volume. So, let's go ahead and find the number of moles by taking the volume times the molarity. So my volume in liters is 0.0416 liters, right? Isn't that 41.1 or 41.6 milliliters? Isn't that 0.0416 liters? Well, multiply it by the molarity, which is 0.100 moles of HNO3 per liter of solution. So liters cancel out, and I'm now in moles of HNO3. Step 2 is done. Step 3, let's get into moles of what we're after. We are after KOH. So let's multiply by a conversion factor. We'll get rid of moles of HNO3, and we'll get into moles of KOH. And that's a nice pretty 1-to-1 mole ratio, isn't it? They're not always 1-to-1, but in this example they are. And then finally, step 4, we'll get into our appropriate unit. Now I want to know the molarity of that solution. Now the molarity is the moles divided by the liters. I know moles of KOH. I'm in that unit right now. So all I need to do is divide by liters of KOH, which I've been given right here. Isn't this equal to 0.0156 liters? So we'll divide by 0.0156 liters. The unit I have left over is moles divided by liters, which is molarity. So we'll get our calculators out. Let's press a few buttons here. Okay, kiddos? 0.0416 times 0.100. And then we don't have to multiply or divide by 1, but we will divide by 0.0156. We'll out 3 significant figures, and it looks like I get 0.267 moles per liter. So the molarity of my potassium hydroxide solution is 0.267. Now, it's one of the most common titrations we're going to do. In fact, in the video I have coming up for you in just a minute, that's what we're going to do. Alrighty, let's do one more problem before we go to that video. Let's do example 13. This says, what volume of 0.050 molar sulfuric acid is needed to completely neutralize 25 milliliters of 0.026 molar sodium hydroxide? Now, you do step 1 by yourselves, then come back to the video and see if you did it properly. Okay? See you in a second. Alright, step 1. Let's write the balanced equation. H2SO4 and NaOH. Aren't those my 2 reactants, kiddos? Now these are all double replacement. Na plus will get together with SO4 negative to form Na2, SO4, and H plus will get together with OH minus to form H2O. Did you notice that you had 2 H pluses here? So you're going to need 2 hydroxides, aren't you? So we'll balance it by putting a 2 in front of sodium hydroxide, and we'll end up making 2 waters. Okay, step 1 is done. I've balanced the equation. Step 2, let's get into moles of something. Now I only know the molarity of the sulfuric acid. I don't know its volume. That's what I'm asked to solve for. But I do know the volume and the molarity of sodium hydroxide. So this volume in liters is 0.0250 liters. So 0.0250 liters of sodium hydroxide. We're going to multiply by the molarity, and the molarity is 0.026 moles of NaOH per liter. Liters cancel out, and that gives us moles of NaOH. Step 2 is done. Step 3, let's get into our desired unit. So we're going to get out of moles of NaOH and into moles of H2SO4. Now in the previous example, that ratio is 1 to 1. But in this example, do you notice that that ratio is 2 to 1? So we have 2 moles of NaOH to 1 mole of H2SO4. So moles of NaOH are gone, and I'm in moles of H2SO4, and I want to find the volume. So we're going to put moles of H2SO4 on the bottom so we can divide out of it, and we're going to find liters. And we're going to use the molarity as a conversion factor. Isn't the molarity 0.050 moles per liter? So moles of H2SO4 are gone, and now we can do our math. So I'll pull out our calculators again, folks, and we're going to start with 0.0250 liters times 0.026 moles per liter divided by 2, because that 2 is on the bottom, kiddos, and divided by 0.050. Now this time it looks like we're only allowed 2 significant figures. I get 0.0065 liters, which is the same as 6.5 milliliters of H2SO4. Okay? Alright, go ahead and watch the video on me doing a titration for you. And then we're going to do a couple more of these practice problems, and I think you'll get the hang of it. All right? See you soon. Enjoy the demo. Bye-bye. Okay, welcome. Today we're going to be doing an acid-base titration. We have some pretty standard equipment here. We'll be using these burettes. We'll talk about how those are used during the experiment. We have a 125 milliliter Erlenmeyer flask, some phenolphthalein indicator, some 0.100 molar hydrochloric acid, and then we have a bottle of distilled water. Now the first thing we're going to need to do is to fill our burettes. We'll actually have had them cleaned. They'll have been rinsed with the solution in which we'll be titrating with. So what you'll need to do is you'll have to top them off and take what's called an initial reading. So on the right hand side we are going to be using base. So you'll take your base and you will simply fill this up past the 0 mark on the burette. Actually, we'll go just before the 0 mark since the tip of the burette's already filled. And then on the left-hand burette, we'll do the same thing, but of course we'll use our 0.100 molar hydrochloric acid. Remember, keep the acid on the left. If you get those mixed up, we'll end up with some problems. So now our initial reading is taken by reading the bottom of the meniscus on our burette. So let's see how I can get this on video for you. I'm going to put a piece of paper behind this for you so it becomes easier to read, and you'll see that that reading, it looks like the bottom of the meniscus is between the 0 and the 1. It hasn't quite reached the 1 yet, so the initial value would be 0 point something. If I read the bottom of the meniscus, I'm going to get 0.9, and I can estimate the last digit, maybe 0.91. for my initial base reading. For my initial acid reading, let me turn the burette so we can read that. It looks like that's going to be between 1 and 2, so I'm going to call it 1.16. So I have my initial acid and my initial base value. Now, we're going to need to put some acid in our flask, and we can rinse this out with distilled water. Doesn't make a difference if it's dry. And we'll put that under the burette for our acid, and we will obtain approximately 25 milliliters. So to open up our stopcock, when it's perpendicular, it's obviously in the opposition, and when it's parallel to the burette, we've opened it up. So right now the acid is entering the flask. I'm not sure if you can see that or not. We want to get approximately 25 mils. I'm going to stop this right around the 26 mark on my burette. I'm not sure if you can see it draining there. So we'll stop it right around 26, give or take a little bit. It's not really that important. So we have approximately 25 milliliters of acid in our flask. Sort of hard to see that volume, so we're going to add some distilled water to this. Doesn't make a difference how much. Think about it. If I add distilled water to my acid, have I changed the amount of acid that's in there? No, I still have a certain volume of acid in there. I've just diluted it with a bit of water. Now we need to neutralize this with my sodium hydroxide. So to do that, we're going to add 2 drops of our phenolphthalein indicator. Phenolphthalein, as you know, is colorless in an acid solution, and it becomes bright pink in a basic solution. So you'll see, obviously, we have an acid solution here. We'll put that underneath our base burette, and we will start titrating. Let me get a piece of white paper for you. Put that underneath here so we can see the color change. Let me zoom in on this as we do the titration. Hopefully you can see that. And we'll start adding our base. We've already taken an initial reading of both. And so as we add our base, you can see the pink color is there for a moment. Where it's highly concentrated in base. But you'll see that as the base molecules come in contact with acid molecules, they're neutralized, and the pink color quickly dissipates. What we'd like to do is to have that pink color stay for 30 seconds, and we want to get it to the exact drop. So we'll continue to add, and let's see what happens here. Getting fairly close to my endpoint. The endpoint is when the color changes there, and it stays at least for 30 seconds after swirling. So getting closer. You can see this is pretty easy to do and actually sort of fun. So it's staying a bit longer. I'm getting very close to my endpoint, and there we go. So I've overshot my endpoint. Please do not discard your solution. If you overshoot your endpoint, you can just add more acid. Remember, we haven't taken a final acid reading yet, so I'm just going to add a little bit of acid here. Not too much. We'll swirl that, and there we go. The pink color's gone, so now it's acidic. And we'll continue to add at base. This time we'll do it a bit more slowly. Just a couple of drops there. Almost. A few more. Once again, we want to continue doing this until we get that pink color to stay. And once again, the objective is to get it to the perfect drop. Okay, now I passed it again. No big deal. We'll go back to our acid. And I'm just going to add a couple of drops. I'm very close to my endpoint here. All right, now we're going to add our base drop by drop. And we'll see what we have here. There we go. There's 3 drops and a hanging drop. We'll touch the side and catch that. And I'm not quite sure that's to the exact drop, so what I'm going to do is I'm going to add just 1 drop of acid. Good hand-eye coordination is helpful here. There's 1 drop of acid, and you can see it's gone colorless again. So we will add just 1 drop of base, and then we will take our final reading. I hope if I can get 1 drop here. If not, we'll have to add more acid again, won't we? So I know I'm very, very close to my endpoint. Let's see what happens here. There's my drop. And let's see. We'll swirl it. If that color stays for 30 seconds, we know that we've reached our endpoint. So, I'm pretty confident that we've done it. So we'll go ahead and we'll take our final base reading, and then we'll take our final acid reading. So we'll look at the burette again to make sure we can read this. So it looks like we're between 30 and 31. So it's going to be 30 point something, not 31 point something. So we can estimate 1 digit. Looks like it's a little bit more than 30.5. I'm going to go 30.55 as my final base reading. And then we'll swing around and we'll do the same thing for my final acid reading. And let's take a look. See what we get for our final acid reading. Let's position this so we can read it. It's best, of course, to get eye level with this, and I'm doing the best I can with my camera here. We're not getting very good focus here. Let me zoom back out just a little bit. See if we can get that. Okay, it looks like it's between 27 and 28. So we're going to call it 27 point. Let's see, 27.85 would be my final acid reading. So we've finished our titration. You guys know the molarity of the acid. Once again, the acid was 0.100 molar hydrochloric acid. We do not know, of course, the molarity of the base. That's the objective in the first part of this experiment, and that's to find the molarity of that base. So you now have enough information to do that. Think about this. You know the initial and the final base reading. So you know the volume of base that was required. And you know the initial and the final acid volume. So you know the volume of acid that was used and its molarity. So with that information, you should be able to calculate the molarity of your sodium hydroxide solution. We call this process standardization. And in your experiment, you'll be required to do this 3 times and take an average. Now, I did this earlier today in my classes, and we were getting 0.0907, right around there, 0.0907. Go ahead and try that calculation on your own and see if you get the same answer as I did. And once again, uncertainty lies in the last digit, so I would feel really good if I got 0.0909 or 0.0906 or even 0.0910 or something like that. We can be off in that very last digit. Alrighty, I hope you enjoyed this. It's pretty simple. You guys will have fun doing this, and it's a skill that we use quite often in the first year chemistry lab setting. So thanks for tuning in. Bye-bye.